good evening or good day, depending on where you are. We are going to talk about the design idioms from alternate universe in this talk. This is the official, my personal slide, so I didn't want to remove it just to have the CppCon one in the beginning. First, a little bit about myself, as it is customary. I'm a senior software engineer at CppCon. I also wrote a book that you might have heard of, Functional Programming in C++, which is available in several languages. Apart from that, I'm a trainer, consultant, KDE developer, and a bit of a university professor. So I'm going to start this talk, since it's called as it is called. First, I'm going to explain what I think that software design is and why this is from alternate universe. So in this picture, you can see two famous people. Obviously, everybody knows about Dennis Ritchie, and not many of you probably have heard of Doug McIlroy. I would say that Doug is the father, well, not of composition, but of the cool composition. He's the father of Unix shell script, so the shell piping. For those of you who don't know this example, a long time ago, he was, let's say, in a code battle with Donald Knuth, which is an amazing thing to be in, right? Battling Donald. So the task was you should parse a text, and you need to calculate for each word in the text its frequency. And Donald Knuth wrote a beautiful Pascal program spanning a dozen or so pages. And then Doug McIlroy came and wrote a 6-line shell script or 6-command shell script that did exactly the same thing. Obviously, it wasn't as performant as Donald Knuth's version was, but dozen pages versus 6 lines. This quite shows how composition can simplify your code and how powerful things like collection processing ideas are. He is the father of the Unix ideology, so you should write your programs so that every program does exactly one thing and nothing more. And the programs should be pipeable, so you should think about output of every program should be acceptable by input of any other. In our use case, we're just going to switch program to function, and we get the software design. So I would say that software design is really about composition. If you hear somebody saying it's about abstractions, yeah, sure, but you build those abstractions in a composable way so that you can apply them to different types, to different algorithms, etc. Obviously, somebody will say it's about components and decomposition, but again, you're writing those components in order to compose them later into one big, beautiful program. The same goes with decoupling. Now the question is, why is this called from alternate universes? When I was invited to give this talk by Klaus, he asked me to give a talk about functional programming, software design idioms. And I don't really think that there are strictly functional programming and object-oriented worlds, etc. It's just that some ideas were born in one world and some ideas were born in the other. So in the usual object-oriented world, we have this world that is currently on the slide, and we can change it, we have getters and setters, and so we can change anything in the world. With functional programming, although I'm not a purist, so I don't strictly think that purity is the biggest thing in functional programming. Usually a lot of design ideas come from the fact that you cannot change the world. You can just create new worlds with something changed in them. So you always keep the old world around. Obviously, if you don't need it, it will be forgotten. In some languages, garbage collected. In C++, obviously, destroyed in some other way. So if you wanted to compare object-oriented world with the functional, just this concept, instead of having set property as a setter, we would have something that is called with property, and it would accept an object and what needs to be changed in that object, and it will return a new object. Now, obviously, in C++, that would be really, really inefficient. So that's the reason why I wrote ref here, just as an idea that you can still have, let's say, pure like API, but perform changes in place. If you want to hear more about it, I've given a talk at the CPP Italia move-only types can save the API. The reason why I'm not covering this here is that obviously there isn't enough time. And I just wanted to show this signature so that you get into the mindset of everything that follows. Obviously, I'm going to use the same ideas in the rest of the presentation, but everything that I talk about would be possible to implement in this way as well. It's just that I find when I talk about different ideas, I find this notation a little bit more intuitive to present. As I said, you can always switch everything to the usual object-oriented notation, and it will still keep working. Now, this talk is obviously, since I don't really have several days to cover all the topics in detail, this will be a higher up overview of several ideas that are usually connected with functional programming. We are going first to start with something that I think that if you don't hear any part of the talk apart from this one, you should just remember this, and you can ignore everything else that I say. But at the same time, this is not really that connected to the rest of the presentation, so that's the reason why the presentation is currently in the dark mode. When we try to do some things, we often see a recommendation, use composition over inheritance. And you can hear that in Java world, in C++ world, especially if you try to inherit from standard, anything from the standard library, etc. Now the question is, what is composition in this case? Word inheritance, since we have multiple inheritance, is also some kind of composition. Obviously, the composition that people think about is create a structure or a class and put a lot of data members inside. This is one way to compose types. This is true, but this is maybe even as problematic as inheritance is. Obviously, well, not as, but close enough. If you see a struct like this, so you have a state, for example, you have a program that wants to count the bytes on a web page. So you need to connect to a web server and then count all the bytes. And when you have finished, you report that count. And you create member variables. Have I started my counting? Have I finished my counting? What's the current count? What is the URL that I need to access? And obviously, you save the socket. Now, before you start, there is no point in having the count variable. Before you start, you don't have a socket. While you're counting, you don't really need the URL anymore. You have the socket. And when you have finished counting, essentially you don't need anything here apart from the count variable. And at that point, since you're no longer going to change it, you just need, you can just declare it as const. So if we just put all of these things that are not really needed together at the same time, we are going to create classes that are easily made invalid. So we can say we haven't started, but we have finished. We haven't started, but the count is 42, and whatever URL and web page socket are at this point, it's still an invalid type. I want to quote Arne Merz. When classes have an isValid method or similar, the code using them is often less clear and harder to maintain. If possible, validity should be an invariant. And this is something that you should always live by. Instead of creating a single structure and putting everything inside it, you can just create different structures for different states that you can be in. And you create an init t, running t, and finish t with exactly the member variables that are needed for that particular state. And then you can compose those types into a big type with std variant that will ensure that you are in one of those and never in anything else. Obviously, you can be empty by exception, but we are going just to ignore that std variant has something strange like that. And this is another way to compose types. The usual one that we've seen previously is called product types in the alternate universe. And this one is called the sum types. My advice is whenever you design any class that you need, just think about which members should be used together and which members should not. What are the benefits? In the ideal case, you can no longer have any invalid states, or you significantly lowered the number of invalid states. Member functions, you can create them to be per state instead of them existing. For example, if you want to start counting, the member function start counting should not exist in any state apart from initial state. But the best one is that this way the C++ really shines, because in the previous approach where everything was in a single structure, you would need to manually close the socket when it's no longer needed, etc. And in this case, whenever you switch the states, all the member variables from that state are going to be automatically destroyed. So you have proper RAI. And these types can be handled easily with std visit and overloaded lambdas. So this was about composing types. Obviously, Steve Downey had a really nice talk about more ways to compose with recursion and etc., etc. Obviously, check that out. But if anything that you need to go and remember from this, I don't want to say the whole CppCon, but at least from similar talks to mine, just please remember that std variant can make your programs much, much, much more safe. Now, we can try to combine or compose types and functions. So at some point, we realized that our state, we actually need an empty state for some reason, and we can create our new type based on variant and say just std variant state t or empty state. So again, we choose from two different, let's say, substates. One is what we previously defined, and the other is we don't have any state at the moment. Obviously, we have the type that does just exactly that, and that's std optional. Now with, sorry, wrong key pressed. We have a bunch of functions, whether they are member functions or non-member functions, defined on that state. Now the question is, when we create std optional or state t, should we just throw all those functions away? How do we usually use std optional? We have something that looks like this. Either we have functions that provide an alternative value. So if the optional was empty, let's consider it -1 or something like that. And obviously there is a member function called value or inside of the std optional, which would provide you exactly that. So default value if the value is not present in the optional. But usually you don't really use that in the code. You often have functions that explicitly check the state and do something in the else branch, etc. So even if there is a value or, it's rarely used because the functions are implemented in the wrong way. The second option is you can have functions that manipulate the value inside of the optional. So if the state is empty, then return an empty optional because we didn't have anything to process. And otherwise, get the value, do something with it, and return it wrapped inside of an optional. And the third approach are functions that do both. I'm going to quote Tony, really controversial tweet that he posted. 9 times out of 10, a for loop should either be the only code in a function or the only code in the loop should be a function. I'm just going to paraphrase it and say, if you're dealing with optionals, your functions should either start with return an empty optional if the original was empty, or you need to use the previously mentioned function value O. I apologize for the jumping between the slides. I had to switch the PDF presenter quite to something that I'm not really accustomed to. So you should never have functions that are of the third type. You need to have functions in the first one which use value or in the second one which immediately return if something is not present. For the functions that do something with the value inside of the optional, you can create a transform function which will behave exactly like for transform behaves with collections or ranges. So you give it an optional, you give it a transformation function. And if the optional is empty, obviously you return an empty optional. Otherwise, you return an optional that contains the result of when you invoke the provided function with the previous value inside of the optional. And this is an abstraction. So we have realized that our second type of functions are usually something that can be done with a simple lambda on the value inside of the optional. And then we have refactored the common code, which is exactly returning an empty optional if the original optional was empty, and then returning the transformed value. Now, this is something that comes from, again, the alternative world or the world of functional programming. But this is something that people have realized is useful even for us. So in C++23, you're going to have a member function that is called transform in std optional. And you will be able to pass it a lambda or any kind of callable to transform the value inside of the optional and get the result. Obviously, I prefer non-member functions because they can be made generic. So this is kind of like the story about std begin versus axis.begin. But it's nice to have both so that you can use whatever you want. Now, we have seen that we can use functions that are previously implemented for the state t that we mentioned earlier, just by putting them inside of the .transform or the transform non-member function. Now, if we want to forget about the values, we can just say, okay, can we somehow make all the functions that work on the state to also work on optionals? And we can use something that is called lifting. So for each function that we have in the state t, we can just call this lift to optional, and it will give us a function, equivalent function that works on optional state t. Obviously, until we get proper compile time, code generation and introspection, etc., this will be a manual process. But once we get introspection, then you would be able just to write for all member variable member functions inside of some type, create a new structure that lifts each of those, and then you get all the functions that work on std optional directly. So if you wanted to just jump out from the optional world, we can see tasks and futures, and we can define transform on tasks and futures in a similar way as we did with optional. And to show a little bit of C++20, how we can do it for anything that supports coroutines, we can just co-await specific task, we get the value. If the task didn't return anything, we are not going to return anything. This coroutine will just end and return an empty task. If the value appears at some point in the future, we call the function fun on it and co-return the value. And again, we get the task that contains the transformed value. And this is essentially the same as optional, expected, etc. And what's more, for optionals, for expected, although not really for STD optional and STD future expected, you can create, you can add support for coroutines so that even this syntax with coawait works with optional types, which is quite cool. And for any type, just lifting would be essentially implemented in the same way as it was implemented for optionals. We just return a lambda that transforms an optional task or whatever. And in the alternate universe, this is called a functor. So if we have lifting and we have a world, we know how to say winter is coming for that world. I know that the reference is quite obsolete and outdated, or we know how to rule the world. Then if we have an optional of the world, again, if there is something in that optional, we know how to rule it. Also, we know how to switch it to winter. If we have a future of the world, we know how to rule the world at this point in time. So obviously, when the world comes out of the future, we will know how to rule it at that point. Or if we have a multiverse with several worlds, obviously if we know how to rule a single world, we'll know how to rule all of them. So we don't need to implement all of these functions. They can just be lifted from the original implementation of the function rule. So let's go even more abstract. So we've seen that for functors, we have something that somehow has a value inside, whether it's a value that exists at this point or in the future, or there are many values that will exist in the future. It needs to read the old value and then to apply an update function to it and generate the result as a new value. We can split those operations into two parts. Just like we have getters and setters for objects, we can have this split into views and updates. The view is going to be essentially the same as the getter. Update is going to be a little bit different. Update is a function that doesn't just take the new value, but it can also accepts the old one and returns the object with something done to the old value. And this idea is called lenses if you want to research it a little bit further. So if we want to compose these functions, so these lenses or properties, we have one property. So this is just the getter function. If we have a getter that retrieves us the inner value from the outer value, and we have another getter that gives us value from the inner, then we can just compose them as normal ordinary functions and get a new property that will directly give us a value given the outer object. For updates, it's a little bit more involved. So we have a function that transforms an old value into a new value. And we want to get a function that can update exactly that small bit inside of a huge outer object, ignoring anything in between. So all the layers, in this case, just the single layer inner, all the layers between them. So in order to do that, we first need to create an update function for the inner object. And then we can use that as the updater function for the outer object. And the code, it's not really that pretty, but it's not that complex either. In this case, the only reason why I'm showing the code, as I said, I don't really have the time to delve deep into all these subjects, so I mostly don't show that much code in this presentation. You can check out my previous talks. They are usually quite more involved. The only reason why I put this function on the slides is that to note that composition, in this case, is something that looks like a composition for functions, but it's not really. This is definitely not the implementation of ordinary function composition. And to say that usually when you define compositions for properties or lenses, you often like to have composition in two directions. Just like people are often confused when you say compose two functions f and g and apply them on x, people are confused that the f function is applied after g. So even for normal function composition, people often like to swap the arguments. So to be more explicit here, we are going to also just imagine that we've implemented operators greater than and less than to accompany this compose update function, so that we can just flip in which direction the properties should be applied. Now imagine a concrete example. You're a landlord, you have apartments, you have a building, and in the building you have a range of apartments. For each apartment you have a tenant, and each tenant has a monthly payment. So if you compose two properties, tenant and monthly payment, you get a new property that just ignores all the tenants in between. You're just going to get directly from the apartment to the monthly payment, because as a landlord, you don't really care about your tenants, you just care about the money. So you can use this as a function object for accumulate, so for projection in ranges. You go through all the apartments. You initially start with 0, you want to add all the payments, and then use the previously defined property composition as the projector. Now, just a small side note, with functors, the function that you pass to the transform, it can change the type inside of the functor. With properties or lenses, this is not really a necessity. If you have a building with tenants, you can't switch from tenant to a pet or something like that. So you can't switch types in general case. But if you do have generic types, so your buildings are, you have some buildings that work on people, some that work on pets, obviously lenses will continue to work. Then you can pass them a function that converts types as well. Okay, so now we've seen a little bit about how we can compose functions and data, and we have created an abstraction called property. Now imagine that we no longer have a single tenant in an apartment, and each tenant can pay us several times a month if that suits them, not just a single time. So if we have apartments, which is, let's say, a property that maps a building to a range of apartments, tenants that map apartment to a range of tenants, and monthly payments, tenant that maps to a range of doubles. These are not really composable functions. They don't have the same domains and codomains. What we have here is essentially we have a property that returns us a range, and for each element in that range, we have a property that returns us a new range, and again. But if our property doesn't really work on collections, but we have made explicitly the property to work on a single value, is it trivial to imagine that if we have a property that returns us a range, and that property transforms something, that it will be trivial to create it in a different way, to have something that returns us a range of items that we can access via that property. The only difference between these two is the function that you're providing. In the previous case, you would provide an already lifted function that works on ranges. And when you flip, you don't provide the lifted function, just the original function that transforms a single element. So you're able to just flip this with a tiny change in, let's say, the function that you pass to the property. And if you have a range of ranges, it's quite trivial to just call join on them, and to get a single range. And we can repeat this, essentially getting a single range that gives us already transformed items that are nested far down in the hierarchy. So something like this. We don't need to use projections anymore because the properties themselves, when they compose, are going to return us a range that we can accumulate over. So we can just say accumulate over all payments in a building, and that's it. Let's see this with a little bit of graphics. So we have a building. A building has apartments inside. Not all apartments have tenants, but most of them have at least one. And each tenant has at least one payment per month. When we say apartments of a building, we're going to get essentially what you expect, a range of apartments in said building. If you compose apartments and tenants, you're just going to focus on all the tenants inside of the building. So you no longer even think that, you don't even consider that apartments still exist. You just see the building as a list of tenants, or a range of tenants to be more precise. And in the end, if you compose also the monthly payments, now you see the whole building just as a range of payments. Again, you ignore all the layers in between of what you start with and what you want to focus on. And this is one of the reasons why these things are called lenses, because they allow you to focus on a specific part of your structure. Now, we've used just getters or views, but we can also update our structures using the properties. So if you realize that at some point you don't earn enough money, you want to increase all the payments by 20%, you can just say all the payments from a building increase by 20%, and this generates a new building. Obviously, as I previously mentioned, you can switch from this back to the object-oriented world, where you would just have a building.update or something like that, instead of having the old building and then moving it transformed into the new one. Now, in this example, we've retrieved the whole ranges from our properties, but we could also, since ranges support filtering, ranges support take, drop, and all of those really, really nice functions, we can also add that into our property design, and we can just create a really nice SQL-like, but a little bit even more powerful than SQL, a query language for our hierarchical data structures. Now, this was really, really, really abstract, so let's come back to Earth a little bit. So let's get back to normal functions and normal function composition. C++ doesn't really support function composition out of the box, so you don't have an operator that will allow you to compose functions, but it's quite trivial to define a function that composes two functions. You just create a lambda that captures both of those functions, and then when that lambda is invoked, you just call f on the result of g, which is called on all the arguments that are passed to that lambda. Obviously, for this to be properly implemented, you would replace the normal function calls with std invoke, but you get the gist of it. Now, I've been told by Daniela E that we're going to get fold expressions for call operator in C++ 23 or so. So you would be able to write a compose function that doesn't accept just two functions to compose, but any number of functions that you want to add. And the implementation would be quite similar to this one. Now the question is, that's all dandy if you have functions that have suitable domains and codomains. But again, let's get back to range apartments, apartments which don't return a value, but range of values, tenants that don't return a value, but a range of values. So we get functions that are just not composable. Now, if you look at these functions in the context of C++, do these functions have the same domain and codomain? From what I've written here, it kind of looks like they do, but in essence, it's not really true. For each of those functions, because there are not no except, they don't always need to return a value. They can be an apartment or an exception. Tenant can return a tenant or an exception, and so on. If we wanted to encode this properly with types, we could just return optionals. And this is a huge difference. So in the previous slide, we had semantically the same functions as we have currently. Just imagine that I wrote no except on these ones. But one of those is supported by the language, the syntax for composition, which looks normal, which we'll already see in the call operator, and everything just works. But as soon as we switch to a semantic equivalent, which contains a custom type called optional, all hell breaks loose. So function calls, function composition don't really work because you don't have the exact type that a function tenant expects by getting the result of the function apartment. So C++ does support composition of functions that have some non-matching types, but only in the case where you have something or an exception. So if you wanted to make a composition that works for these functions as well, what we can do, we can just create another kind of composition and just say, instead of using the normal function composition, we want this to work on optionals. So we are going to invoke the second function, get its result. If that result was empty, because we can get an empty optional, just imagine exceptions. In that case, the composition as well is going to return an empty optional. Otherwise, we're going to get the result, so extract the result from that optional and invoke the function f on it. Now, since the function f returns an optional of something, optional of C, this means that the whole composition returns an optional of C. And since the initial invocation of G accepts the type called A, this means that the whole composition is a function that maps A's to optionals of C. So this is, again, somewhat of a composition. We get a function, two functions that map values to optional values. And by composing them, we get a new function from a value to an optional value. So this looks like a really nice composition, even it's not strictly the traditional composition of functions. Now, if you remember that we can create coroutine support for optionals, we can rewrite all the code instead of using, again, the mcompose function. We can pretend to use C++ language's support for composing functions like this with co-await. So instead of creating mcompose of apartment, tenant, and payment, we can just say, okay, my apartment is going to be co-await of apartment. My main tenant is going to be co-await of tenant, and this month payment is going to be co-await of payment. And this way, we achieved something that looks like normal C++, just has this one additional keyword called co-await. As far as the semantics of this thing go, any of these functions that return an optional value, automatically our whole function where we wrote this code in is going to return an empty optional. So just like if any of these functions thrown an exception, our function would end without a result and it would throw an exception. So we achieved this exactly same semantics as we would have with exceptions, only with no except. Now for all of the things that support co-await, we can create a more generic mcompose just by reusing the previous one. We can say what? So we co-await the result of the invocation of the G function, and we can invoke function f on that result. And again, whatever co-await means for the specific type that you work on in this code, it will just work as it should. If it's an optional, it will behave as if you're using, as we said, it will be semantically equivalent to having exceptions. If you have std expected, the same. If you have futures that support coroutines, it will be a little bit different, but again, it will have the same meaning. So what will be the meaning with futures? It will be when you co-await, which means when the future arrives, we're going to apply the function f, and the function f is going to return us a new future. So you get composition of futures. And you get composition of quite a lot different fun types in this way just by using co-await and some monadic coroutine trickery. Now, the only problem with this slide is that this doesn't compile. In essence, the reason why it doesn't compile is that if you have a co-await in a function, it's automatically a coroutine, and you cannot use return inside of a coroutine. With coroutines, even if that coroutine as a whole returns a future of something, and even if you have that future in your hands, you cannot say return this. You can just say, okay, extract. I want to return this, but I cannot. So I'm going to extract the value from it, whether it's an optional future or task or whatever. And then I'm going to co-return it. So this is just a little bit a syntactic nuisance that C++ forces us to do. And what co-return will do is get a new future, put on top of that value, and return it as the result of the function. But in essence, it's still quite easy to implement. We just have to co-await 2 times instead of a single time, and return the result. And this way we can, as I've previously mentioned, compose all these strange functions that accept a value and return a wrapped value of some sort. Again, optional, expected, sometimes even loggers, and who knows what. Now, range is a little bit more specific. Coroutines are essentially made for these wrapped types that can contain at most a single value inside. But we can also define similar things for ranges as for futures. So the transform for ranges exists, join on ranges exists, etc. So we would be able to define the same mcompose function for both ranges, for futures, and in the end, even for generators. What can be said about generators, just like a future is a future of a single value, and a range is something that generates values over time. Just imagine those generation of values to be asynchronous, and you get generators. So the functions that are needed for this mcompose to work is a function that takes a value and wraps it inside of something. So exactly what co-return does. You need a transform function, which we have already seen, and we need join. What is a join? If you have a list of lists, you want just a list of all items that were nested inside. Or if you have a future of future, you don't want 2 futures, you just want to have directly a future of a value. The same, there is no much point if having optional of string, it can always be mapped to a single optional of string. And this has the most strange name of all. types that have these and some rules that go along with it are called monads. And the reason why this is not called functional programming but alternate worlds is that we already have quite a few of those in C++, which traditionally is not considered a functional language. So we have optional, we will have expected, we have vectors, we have pairs, which under some circumstances are going to be also monads. We have futures, we have ranges, we are going to get generators, senders and receivers, coroutines, Herb exceptions, everything in this list is some kind of a monad. The only problem that I have with C++ at this stage and regarding this is that a lot of these implement, let's say, 90% of a subset of a monad, and then you get all the implementations completely separate, and every ranges, coroutines, Herb exceptions want to use completely different infrastructure in the compilers, in the libraries, to implement essentially the same thing that could have been implemented as a general thing called a monad. Apart from this, parsing is another really useful use case for monads. You can check out, there was a recent talk, I think, about at Meeting C++ about how to implement parsing with coroutines, which again relies on the fact that parsers can be implemented as monads. Logging, the same goes for logging. So let's get a little bit back to the properties that we mentioned. So we've seen that we can create properties and remove all the ranges from all the properties, just making one top level range. And we mentioned that for that to work, we just had to have the join function and to have lifting, which is essentially transform. Which means that we can use the same idea for all of the other things that we've seen. Just imagine that building doesn't return a range of apartments, but a future apartment. And tenants returns a future tenant, and a payment returns a future payment. By composing these properties, again, just by using these few functions that we've defined that monads should have, we can create properties that, when composed, return you a future of the payment. And again, you don't care about anything else apart from that future payment. The only thing that you need to redefine is the composition functions for properties. Instead of using normal function calls, you would need to use either coroutine-based or any other composition that we've seen in the presentation. So as a short summary, which is not really connected that much to the slides, but some general advice that I wanted to give at the end. First, notice simple patterns. We are kind of used to, especially in object-oriented design, to start from huge ideas. We want singletons, we want factories, we want... Usually when we write code, we have some idioms that we write all over, and we always write 20 keywords for the same thing. Try to notice those things and make an abstraction out of those. All of these abstractions that we've seen are really trivial. Functors have transform, monads have 3 functions, and properties have 2. And you've seen how powerful those simple abstractions with really simple functions inside can be. Obviously, write functions that do one thing and one thing only. Make functions composable, whatever composable means to you. So again, we've seen a dozen different things that we can call composable in this talk. Don't be afraid of concepts with strange names. So when you see something called a monad, a functor, or whatever, just ignore the name, because those names are usually invented by mathematicians that sometimes want to be fun, sometimes want to, I don't know, play tricks with the readers, etc. Sometimes the names have proper meanings inside of maths, but usually those meanings are really hard to translate to the world of normal development. And the last one, and maybe the most important one, don't assume that something is useless because the example is. Often when you hear about strange concepts from the functional world, you're going to try to dig a few examples, and you're going to often find that those things help, for example, Haskell programmers to implement things that we in C++ already have. For example, when you search monads, you're probably going to first to find I/O, and we have normal I/O. When you search for functors, I don't even know what you're going to find. If you try to search for lenses, you're going to learn that the only reason why lenses exist because Haskell syntax for updating nested structures is awful. And then you realize, okay, yeah, in C++ it's just ... and we can update something. So just skip those basic examples. And for some types was one of the worst things that I've seen in my life. And it was usually about implementing inheritance from object-oriented worlds, in the sense that the first thing with some types that you do is always make an abstract syntax tree. And when you see that example, you know how to do it in C++, and you're not going to bother reading the rest of the article. Just don't think that things that have been birthed in Haskell or another language or in another world like functional programming world are useless just because they're trying to use them to mimic something that we already have. Try to think of, try to give them life of their own inside of C++ as well. Now, I wanted to follow the chat, but while presenting, but the font was quite small for me to see. Okay. Should I go through the chat, or somebody wants to put something into the Q&A officially? Okay, so the question, the official one, I'm going to click answer live. Invariant of some types, how can we enforce that we shouldn't go back from running T to init T? Obviously, in the variant itself, you don't have the API for something like that. But variant, like most of the things that the library provides you, is just a building block for something greater. So you can always write some, let's say, extension or something that doesn't really inherit variant, but uses variant on the backend side and make statically compiled checks that check which was the previous state and which state are you going to. I would say just that would be a normal object-oriented way. Just write update functions that make sure that you never go to an invalid state from some of the later states. But that's a really, really good point. Variant can save you a lot of hassle by removing invalid states. As far as the state change goes, you still need to write explicit code which forbids going from one state to the other if that's not a legal change. Also, there was a comment about lenses. When you research lenses, again, you're going to find 10 different names. Some people define it a little bit differently, etc. Usually people couple the updater and the view inside of a single thing that they call lens. Obviously, with all the names and all the people that work on it, you can find some discrepancies, and you can find some similar ideas that work a little bit differently that are called the same or called differently, etc., etc. So just remember the ideas and remember the generic names, and then research and do your own thing and call it as you wish. What books would I recommend for those of us who want to study composability? That's an awful question. I have no idea. You can write to me at ivan@cukic.co. I did have a slide that was meant to show, but it was, okay, I can zoom it in. Okay, cool. Again, the PDF viewer is a little bonkers today. So you can just write me to this email address and I'll try to find something to send you. Apart from that, I've also added a few links into the slides, so you can download those from the CppCon website when they are published. Okay, so another question. In one of your composed slides with co-await near the end, I didn't seem that you used gres, maybe. Let me try to see. Okay, yeah, this needs to be gres. Obviously, we are extracting result from the previous co-await and we want to pass on the result of G to the function f. Did you explore using object instead of object-to-ref and combining that with a fully immutable data approach? I started with using object, but to quote John Lakers, constructors can be expensive. If you manage to write your APIs with just refs everywhere, you don't have a single constructor. Well, you have a single constructor for the initial value, but all the updates are in place. You don't have any moves or anything else. You just have the API that looks like you're performing moves, but just imagine like return value optimization on steroids. With object-ref, you're going to get really a single instantiation and then changes in place just as if you called set. In the CPP Italy talk that I mentioned, you can see the benchmarks that I did by switching from object to object-ref in several functions. And it's quite astounding. Do I have any comprehensive framework for functional programming in C++ to recommend? Not really. Sadly, those things rarely get out of. A lot of people implement parts of something that could be a really nice functional programming framework, but those parts usually end up private in some proprietary code bases, and I have seen a few people try to implement everything, for example, to simulate a lot of things from Haskell in C++, etc. But I can't really recommend any of those frameworks. They're really nice to research and to read how they're implemented. But I haven't found at this point, if you find something, please ping me, something that is production ready and actually used in proper software, C++ software design. So again, I never advocate trying to implement exact Haskell ideology in C++. You should always take all the idioms from other languages and adapt them to be useful for you in C++ and not change C++ as a language to suit ideas from the other languages. As for the fully immutable data approach, I have seen a couple of really nice projects that implemented, let's say, immutable changes that look like usual reactive programming with Juanpe's Immer library. And it can work, obviously, performance penalties, but the code was quite nice and easy to understand, and all the state changes and everything else was quite easy to follow. Obviously, the developers who did it liked to write readable code in any style. So I can't really say that this is because they used immutable data and value-based stuff. is just that it wasn't worse than their usual code.